Welcome back. We're working on using the properties of the continuous time Fourier transform. And in this example, well, this is one of my favorite examples. We have an RL circuit that we can analyze in time or in frequency. And I will remind you that you do not need to know circuit analysis in our course Signals and Systems. Now, I like this example because previous students have told me that this example is eye-opening to them. So hopefully that's the case for you as well. Now in time we can analyze this circuit. We can say something, we can perform KVL, right? Kirchhoff's voltage law is to add the voltage drops across each of the three components in the loop. So for example, we can start at the resistor, although it doesn't matter. And we'll say, okay, we drop by VR, voltage VR, and then we can drop by VL, the voltage across the inductor, and then that must equal the supply voltage V, right? And in a series circuit, the current is the same in each component. And so we can apply Ohm's law for the resistor, and we can say that the voltage across that resistor is I times R, right? And the voltage across an inductor is related to I by the derivative of I. It's L, which is the inductance, times di dt. So you learn this in circuit analysis. It's okay if you don't remember it for our class. And then equals that voltage V. And then you can solve this for I, right? I of t, right? If V is a function of time, right? If it's an AC voltage, then I is also. So you have a first order differential equation here that you need to solve, right? But in circuit analysis, you did not solve that in time. You did not solve this differential equation. I bet I know what you did instead. Instead, what you did was you for some reason you made this capital V. More on that in a second. And then you replaced the resistor with this box, and you still called it R. And then you replaced the inductance with a box, and the impedance of the inductor is j omega L. Okay, so you should have learned that, and it's okay if you don't remember it. But you replace the inductor with its impedance, which is j omega L, right? And so you have this picture, and you still have this voltage drop VR, and you still have this voltage drop VL, and you still have a current, series current, which for some reason you made capital in circuit analysis. And so what you can do here is still apply Kirchhoff's voltage law around the loop. You say VR plus VL is equal to V, same thing as what we have here, but for some reason we're using capital V in this picture. And then the voltage drop across the resistor is I times R plus, and then you can use Ohm's law with the impedance. And we do that, we say J omega I times L, or L times I, all right. J omega L times I, right? J omega L, the impedance, times the current through, and then that gives me the voltage. And then you have an algebra equation. You solve this for I, right? Solve for I. But it's an algebra equation. It's a complex equation because there's J, so there's a real part and an imaginary part. It's complex, but it's algebra. You can factor out an I, and you can solve that for I. So, what did we do here? Well, compare these two equations. Here's the eye-opening moment. If it's going to happen, it's going to happen right here, hopefully. Compare those two equations. Now, we made I capital, okay, and we made V capital, but forget about that for a second. What else did we do? There's one other difference here, and the difference is that we replaced di dt with j omega I. Let that sink in for a second. And I'm going to write the differentiation property down again. If x of t has Fourier transform capital X of j omega, then the derivative of x of t has Fourier transform j omega times x of j omega. This is the differentiation property that we covered. So look at what we did. We said, we're basically saying, all right, if I has Fourier transform capital I, right? That's why you changed lowercase to capitals, by the way. It's because you took the Fourier transform of this equation, of the circuit, basically. So if I, little I, has Fourier transform capital I, then the derivative has Fourier transform j omega times capital I. So all of this is to say that what you did here was take the Fourier transform, right? This equation, equation 2, is the Fourier transform of equation 1, and that's also why the V became capital. You took the Fourier transform. Of course, in circuit analysis, you did not call it Fourier transform. You did it under the guise of impedance. You called these things impedances, and but what you were actually doing was taking the Fourier transform. So why did you do that in circuit analysis? Because the idea is that it's easier to solve an algebra equation, albeit a complex algebra equation, than it is to solve differential equation, especially if we start adding loops, that are related, right, dependent on other loops. It's easier to solve algebra equations than it is differential equations.